So we're in your chemistry, and now we're going into section 4, and we're going to be talking about equivalent masses. And equivalent masses means how many moles of one solution we need to mix with the other mole of solution to be as equivalent, to make them equal. So it says 1 mole of sodium hydroxide, NaOH, will come with 1 mole of hydrochloric acid. Only one protein is released there, so they're equal. They're 1 to 1. Their ratio is 1 to 1. But if you go on to H2SO4, you're going to see, because it says H2, there's 2 hydrogens there. So now with that situation is going to be quite different, because this is diprotic, because it has 2 hydrogens. This one only had 1 hydrogen. So we know now it's going to release 2 protons when it dissociates, because there's 2 hydrogens there. So now we're going to know that it's the ratio to that, and going through that that reaction is going to be 2 to 1. So because you have 2 hydrogens. Remember, that's diprotic, 2 hydrogens, and this one is 1 hydrogen. So this one was 1 to 1, and this is going to be 2 to 1. So as a result, twice as much sodium hydroxide is going to be required. So this one is going to be 1 to 1, and this one is going to need twice as much of this when you're combining, because it has 2 hydrogens. So here it says, instead of dealing with mole amounts of acids and bases, because this is all about moles and neutralization reactions, it is more convenient to use the amounts that are chemically equivalent. So instead of just talking about moles, we're going to be talking about equivalence. Is it equivalent? Actually, it means the number of moles of an acid that will supply it, but they're calling it equivalence. So when they're talking about acids and bases, they're going to say this amount is going to be equivalent to this amount, instead of just using the moles that we're used to. So the equivalent mass of an acid or base is the mass per equivalent of that acid or base. It's so similar to the molar mass, but now it's going to be just what I talked about. How many of the protons of the hydrogen will be required with the base? How many is basically we're going to say. But the mass is now, of course, going to have to be measured in volume. And so you can read through this part right here when it talks about volume, but the equivalent mass, here's the equation. So the equivalent mass is going to take the molar mass of the acid. You're going to take the molar mass to make the equivalent, and you're going to divide it by the number of ionizable hydrogen atoms or base atoms, hydroxide, to produce in the formula. So you're just going to divide it by that to see, and if to see what that mass would be. Thus, the equivalent masses of in these formulas, let's just go through these formulas here real quick, and you can see why. Let's just glance at them, because here you have 3 hydrogens. So that means you're going to take the moles, and we can add the moles up from our periodic table and find, what is the atomic mass of hydrogen and phosphorus and oxygen. We're going to add this up, and we get this number off our chart, right? And then we're going to have to divide it now by, this is triprotic right here, so you're going to have to divide it by 3. So we divide it by 3, and this is the number we get for the equivalence. And this is in grams. So we're measuring this in grams because we're using grams per mole. So the same with this one. We have barium hydroxide, and we are going to see the hydroxide here on this side is 2. So we're going to divide it, because this is a base. Whenever you have the H, it's an acid. Whenever you have the OH, it's a base. So we're going to take this OH, and it has a 2 beside it, as balanced with the barium. And so we're going to find out, what is the barium? We look up the grams per mole. We look up the atomic mass on your chart, and this is what we find. And then we're going to divide it by 2 right here. And this is the answer we're going to get. Okay, on to the mass here, again, nitrate here, so that we're going to nitric acid here. So here we have one, only one. So now we only divide by one because there's only one hydrogen there, so it's going to be the exact molar mass as it was before. The only reason we're doing this with equivalence is because we want to divide these the hydrogen and the hydrogen and the H and the OH in these situations to get, because we have to divide them out. Otherwise, we would just go by the moles. Of course, we're just going by moles. But the only reason we're doing that with equivalence so that we can divide it out to find out how much acid, how much hydrogen, or how much hydroxide here with the base to find out the exact amount you need. Because you're going to need, for this one, you're going to need a lot. With the equivalent here, 32.66 grams are going to be the equivalent. You're going to need 3 times that, right, to make that number. And this one, you're going to need 2 times this to make that number. And this one's going to be equal, 1 to 1. So 1 to 3, 1 to 2, and 1 to 1 is all, in this whole situation. So that's what we're talking about when we're talking about equivalents. Equivalents are mainly dealing with molar masks, but dividing them by the number of ionized H or OH. Here's H and OH. Divide them by that. It's either going to be 1, 2, or 3, this bottom number. And dividing them out, and we'll get the equivalence. So the advantage of using equivalence is that one equivalent of any acid reacts with one equivalent of any base. But we have to know that some of those bases are monoprotic and some are polyprotic, have one or twice as many or 3 times as many. So that's the advantage, because we have to divide it out by those monoprotic pieces. So that's the only difference of equivalent and molar. So okay, normalcy or normality. Normality, I used to call it, pronounce it wrong. Normality is how you pronounce it. The concentration of a solution may be expressed in molarity, the number of moles per liters. The difference between this and this equation that we just did, this is in grams and this is in volume, which is liters. However, it's often convenient to express concentrations of solutions of acids and bases in terms of equivalence instead of molarity. Remember, we don't want to really work with moles anymore, especially when we're working with equivalents. And so the concentration of a solution expressed as the number of equivalents per liter of solution is the normality. It was morality, now it's normality. So what is normality? It's a big N. It's basically taking the equivalents, which we had divided by either 1, 2, 3, whatever this number was, dividing it here, and find that equivalence, and then we're going to put it towards liters, not grams. So this is going to be towards volume, and this is towards mass. Volume is like a liter of liquid or what, and a mass is how much it weighs, really, comes into the density of it, right? Since the number of equivalents and the number of moles are related by the number of equivalents per mole, molarity, normality, they're all related, right? They're very closely related, only we did that division here to find, and so that would be still the main difference. But just think of normality as being equivalents, taking the equivalents here and just dividing them into liters. So it's very important that we know if a solution of acid is going to be monoprotic acid, such as hydrochloric acid, you divide it, the M is going to equal N. Molarity is going to equal M. But it's not going to equal that if it's diprotic or triprotic, right? So normality is going to be the same as molarity right there. But if it's diprotic or if it's triprotic, it's going to change because we have to divide it out here. Remember? So I hope you get this. So we'll probably look at it differently with the applications. Let's see. All right, so let's look at, it says, what is meant by the equivalent mass of an acid or base? I just did that. The equivalent mass is the mass per equivalent of acid or base. you're taking the molar mass and dividing it by the H or the OH, which makes it, that's just what we're doing right up here. This is how we get it, dividing by to the product to see if it's product, dividing by 3, if there's 3 hydrogens, or dividing by, that is going to be the equivalent mass in grams. We're taking moles, just like we do from the periodic chart, and just dividing it by that, and that way we get equivalence. Just an easier way to say how certain acids and bases will react to each other in being equivalent. You might need more base or more acid, depending on the solution having more, needing more hydroxide or hydrogen. So explain the difference between the normality of the solution and the molarity. It's just similar. If the molarity is 1, we have only divide by 1. There's only 1 hydrogen. Then again, molarity is going to equal that. But if it's diproduct or has 2 or 3 triproduct here, then we're going to divide it, and so the molarity is going to be not the same. It's going to be different because it's going to be divided by that. So the label on a bottle of concentrated sulfuric acid reveals the concentration is 18 moles. What is the normality of this solution? Well, let's look, what is sulfuric acid? So if we take sulfuric acid, we'll find that it's any type of sulfuric acid. Here's sulfuric acid right here. Its is 2. It's 2 per molar. So then we just take its concentration now is 18 moles. We're going to have to times that by 2. So we're going to get, it's now 36 because it's 2 equivalents per mole. So it's going to be 36 moles. To get the 18, you're going to have 36. So because it's diproduct. Now, what is the normality of this solution? Find the normality of a solution that's 18 moles solution of hydrochloric acid. So hydrochloric acid, because it's just 1 to 1, it's just going to be 18. So the moles are going to be, find the normality, it's going to be, 18 to 18, right? And this is going to be 36 to 18 because it has it has 2 H's in it, the difference between those two. It's kind of, just have to think, it's kind of easy to think. It's just basically if you're in the laboratory, you need to know how much acid is going to react to how much base. And they can figure it out by the equation here and how much hydrogen is required in the molecular formula, right? So, okay, let's go on. I'm going to stop there and we're going to go on now. That's just now finding masses, but now we're going to go on to pH. And I think I should do that in another video.